Hello all, I hope things are well. I want to take up a question from the homework and then I'm going to move on to our last topic in thermal chemistry, thermal physics, thermal energy, which is about heat and thermal energy. So the question I'm going to do from the homework is question 32 from our textbook on page 276. Question 32 reads, a duck wants to take a bath, fills a tub with 50 liters of water at 38 degrees Celsius. After taking a phone call from his friend, the bath water had dropped by 10 degrees to 28 degrees Celsius. It says now you're going to just want to warm up your tub, so you put the hot water and you turn it on, and it says how much hot water do you need to add to get it back to 38. And we're told that the hot water is 80 degrees Celsius. So what I'm seeing here is a hot plus cold. My hot is water. My cold was cold water. Whoops. Now we're told the amount of cold water that was in the tub was 50 liters, which is 50 kilograms. Okay, a kilogram is a liter, so my mass is 50 kilograms. If I look at my hot water, mass is unknown. Now, I know that they're both water, so they both have the same C value, 4.18 times 10 to the power of 3 joules per kilogram degree Celsius. And the C here is also 4.18 times 10 to the third joules per kilogram degree C. So those are my C values. I know the starting temperature of the two before I mix them. Temperature of the hot water was 80 degrees Celsius. Temperature of the cold water was 38, but now it's dropped by 10 degrees, so it's now 28 degrees Celsius. And I know my goal here is to get back to the proper temperature of my bath, which is 38 degrees Celsius. Notice that in coming up to 38, that cold water is going to be gaining thermal energy. The hot water at 80 degrees is going to be losing energy. So as I put it in, as the hot water cools, it's giving its energy to the cold water. Right? And what I know is that the temperature, thermal energy or heat lost by the hot is equal to the heat gained by the cold water. And remember, I need that negative sign in there to make it work. Remember, my whole goal here is to get to 38 degrees C. Now, I know that to calculate my lost, I'm going to use MC delta T. To do my Q gained, it's MC delta T with a negative sign. I'm going to put my mass in on the left, which is unknown. My C value is 4.18 times 10 to the 3. Delta T is T2, 38 minus 80. On the other side, I have a mass, which is 50 kilograms. Need a negative sign in there. Don't forget my negative sign. Times the C value, 4.18 times 10 to the power of 3 times my delta T, which is final, minus initial. Notice that I've got 4.18 times 10 to the 3 here and also over here, so I can cancel them. Just get rid of them, make the math a little bit easier. So what I have on the left now, 38 minus 80 is negative 42 times the mass of the hot is going to be equal to 50 times plus 10, right, because 38 minus 28. And then if I my calculator here, I end up with negative 500 on the left divided by negative 42, and I get 11.9 kilograms. Or 9.8 liters, or 11.9 liters. I don't know if it asks for volume. How much more hot water would you have to add? It doesn't really matter, obviously, because a kilogram is a liter. Okay, so Q equals MC delta T. And again, we use that type of question quite often in the real world, right, when we're trying to heat something up. Okay, I want to go back and look at my final note in this section, which is what happens when something changes state. When it changes state, so if I've got an ice cube and I put it in a glass by itself, so I just take a glass, I put an ice cube in, and I come back a few hours later, and the ice cube, which was originally at -4, let's say, coming out of the freezer, and I come back and the temperature has changed to get to a final temperature of room temperature, say 20 degrees Celsius. Now, if I was able to watch that process happening, I would see over time that the temperature that started at -4 degrees Celsius coming out of, or let's say -10, let's say my freezer's at -10. Try my other pen here. I'm going to go from -10, and I'm going to go all the way up to 20 degrees C. -10 degrees C to 20 degrees C. So here's my ice cube at -10, and as time goes by, it's going to go up in temperature until it gets to 0. When it gets to 0, it's going to melt. As it's melting, there is no temperature change. Now think about what's going to happen here is I can have ice at 0 or I can have water at 0. Okay, what happens between this point right here and this point right here is I'm going to have a mixture of ice and water at 0 degrees. On the left end, it's going to be almost all ice. As I get closer to the right, I'm going to have more and more water until I get to the end when I have all the water, all the ice is gone, and now, sitting on the counter in a 20-degree room, temperature is going to go up by 20 degrees Celsius until it gets to the final temperature. So 3 things had to happen here. Let me just erase this arrow for a second. So I've got 3 things happening here. Okay. A, B, and C. I know that in A, there's a temperature change. And so I know this much. I know that it's ice, which has got a different C value than water. So I'm going to have to look up my C value, and I know what the mass is for my block. So I can calculate QA. For C, I have MC delta T. I've got a temperature change, right? I know what the temperature change is. It's going from 0 up to 20. I know that what the C value is because it's liquid water, 4.18 times 10 to the third. And I know the mass of the ice. So I can calculate QC. Question is, what happened between A and C? Right? Did the ice stop absorbing energy? No. So was there still a Q value? Yes, I'm still transferring thermal energy to that ice as I'm continuing to melt more and more of the ice until it's gone. Right? All the way through this little section right here, I'm going to continue to add ice energy to my ice, but there's no delta T. So for QB, okay, I can't do this. Something is wrong with this equation because there is no, there is no delta T, which means delta T is 0, right? From A to B, delta T is 0, went from 0 to 0. So the temperature here must be 0. The energy added must be 0 if this is the equation. However, I know two things. Number one, delta T is equal to 0. Delta T is equal to 0, and I know for sure that Q is not equal to 0. Think, okay, mathematically we have a problem, right? The problem is this is the wrong formula. This formula does not work when an object is changing state. So what we have is a new formula that we're going to be using for today's note. Okay, and the formula is Q is equal to M times L. Now what is this telling me? It's saying that when, sorry, we're using capital L in this book. What L is a number called the specific latent heat. Latent means hidden, right? So hidden means, what's hidden? Well, what's hidden is the fact that I'm adding energy to something, but it is not changing in temperature. I'm adding thermal energy, but there is no change in temperature, right? That energy that I'm adding is hidden, right? We don't see it in terms of the thermometer. However, we would see it if we were looking at the actual change of state that was going on. Now, it turns out that L is called a specific, just like C is called a specific heat capacity. Specific heat capacity means it's specific. It depends what kind of matter we're talking about. Liquid water, solid water, steel, copper, aluminum, air, oxygen, right? We know there are different C values for different types of matter. It is specific, right? This is the same. This is specific latent heat. And what that's telling me is that there's a different L value for different types of matter. So when this ice cube is melting and turning into liquid water here in region B, right? I can calculate the amount of heat by looking at this number here. So the L value for this is 3.3 times 10 to the 5 and the answer is in joules per kilogram. 3.3 times 10 to the 5 joules per kilogram. I need to get that number from the textbook. There's a table on page 266 and it tells me what that L value is. So if I know the mass now, and I know that it's water that is melting, other things can melt, iron can melt, copper can melt, wax can melt, right? All kinds of things can melt. I want to specifically talk about water melting. So I'm going to look at the L value and I can just determine how much heat did I need. I don't need a temperature, anything to do with that, because I'm not interested in the temperature. All I care about here is that I'm switching from a solid to a liquid. Now it turns out that if I was to take that ice cube now, and maybe I wasn't just watching it sitting on the desk, but maybe it was actually in an oven. And in the oven was set at 150 degrees Celsius. Well, what would happen to that water? It would go up 10 degrees, 10 degrees, 20 degrees, 40 degrees, 60 degrees, 80 degrees, 100 degrees. What happens at 100? I'm going to start watching that water boil. Is the temperature going to go any higher? It is not going to go any higher. Water can never get to 101. Right? Once it gets to 100, that's it. It's got to stop increasing in temperature, and any additional energy that I add to it is going to cause to change state again. Right? This time it's turning into a gas. It's going to evaporate. It's going to boil away. And if I could collect that gas in a container, in the oven, I could now continue to heat that gas. Until I got up to a final temperature of 150 degrees Celsius. Noticing that at 100 degrees Celsius, I had something else going on here, D. And then in E, I would have a Q equals mc delta T again. So I can go back and I can calculate Q for E which is mc delta T. I know the mass of water was given to me in the question. I know the C value for steam, right? In my textbook, again, I can look it up. For steam, it is 2.0 times 10 to the power of 2 joules per kilogram degree Celsius. Okay, notice that that's very different than water. Water was 4.2 times 10 to the third. Oh no, steam is actually, that's a mistake in the textbook. It should be 2.0 times 10 to the third power joules per kilogram. I'm going to suggest you go back. If you've got a textbook, you can actually write in the textbook, change the C value for steam to 2.0 times 10 to the power of 3. That's a typo in the book. Your book is probably already corrected. Mine at home, I haven't actually written it in, so I don't usually use this book. But anyway, so I now know C value for steam, which is different from the C value for water, which is different from the C value for ice, right? All these different states of matter for water have their own C value, and I now know delta T because I'm going from 100 up to 150 degrees, so I've got a delta T of plus 50, and I can go ahead, I can calculate QE. Okay, the question is now, what happened in part D? Well, in part D, I had a change of state again. So notice that I can't use mc delta T again because there is no delta T, right? Just as much as I had before, if I've got no delta T, that would tell me that there was no thermal energy added, but I know I was heating it, right? So if there's QE, but the delta T is 0, that's telling me again, this must be the wrong formula, right? So the formula that I have to use is the same formula that I had before. Q is equal to m times L, the one that I've got down here for when I had a change of state for water before. Now I've got a little bit of a curveball here, right? The L value for water turning into steam is not the same 3.3 times 10 to the 5 joules per kilogram. I have a new L value that I have to use here, and again, it's in the textbook. It is 2.3 times 10 to the power of 6 joules per kilogram. Okay, 2.3 times. Notice that the last one was 3.3 times 10 to the 5. This is 2.3 times 10 to the 6. Now, again, I'm seeing, okay, this is highly confusing because I've got Q equals ml here, and I need to use this L value. I've got Q equals ml here, but I need to use a different L value. So how do I know which L value to use? Well, in our textbook, we've in physics, we've denoted 2 different ways to describe L. Whenever I'm switching from a solid to a liquid, or a liquid to a solid, we call it specific latent heat of fusion, LF. And if I'm switching from a liquid to a gas, or a gas back to a liquid, I'm going to have to use the specific latent heat of vaporization, or LV. So my LV for water is 2.3 times 10 to the 6. My LF for water is 3.3 times 10 to the 5. So again, you'll see when you look in your textbook the different C values the different L values for different types of matter. Okay, and we need to use that. So let's go through our note here. Okay, so it says, until now, we know that if we add or add energy, we have a temperature change. So we can use mc delta T. Temperature change means a change in the kinetic energy of the particles. Okay, remember, kinetic energy is a reflection of the temperature of the particles. Right? More temperature means the particles are moving faster. Now, I know, as we've just seen a moment ago, that when an object is changing state, right? Whenever I've got that change of state going on, right, whether it's solid to liquid or liquid to solid, it's going to need a different formula, and I'm going to use Q equals ml. So when I'm warming ice, so in this case, I was warming ice from -20 up to 0. Okay, and when it gets up to -1, I have a nice straight line that shows that as I add more energy, as time goes by, I have this nice straight section here, A. Not very straight on my graph, but it should be nice and straight, showing that as time goes by, if this is a graph with sorry, not delta t, with t on the bottom in seconds, during region A, I'm causing it to warm up. Okay, and it's a direct relationship between the amount of energy added, which is a function of time, and the amount of temperature change that's going to happen. Now, if I continue down here, it says Q equals mc delta T works absolutely perfect for determining the amount of energy. Okay, and that continues to go on until I get to 0 degrees Celsius. And now, any more thermal energy is going to cause that melting to occur. And through the melting process, I'm going to have a mixture of my water and ice. And as I continue to add energy, there is no delta T. Right? So the energy is hidden energy. Right? It's hidden heat. Because I'm adding energy, adding heat, but it's not showing a temperature change. So for my heating graph, you can see here at the bottom that you can see that as I heat it, the ice will go from -10 up to 0, then more energy will be added. Time is going by, I'm continuing to heat it, and nothing is happening to the temperature. And then I'm going to continue to heat the water. Then I'm going to turn it to vapor, to steam, and then I'm going to warm my steam up to the final temperature here on this graph of 110 degrees. So what we now need to do is look at how much energy was required to melt 1 kilogram of ice. Our textbook uses 3.3 times 10 to the 5 joules. I won't mark it wrong if you use 3.4, depending on 3.3 times 10 to the 5 joules, right? And that's for 1 kilogram. In other words, 3.3 times 10 to the 5 joules per kilogram that melts. Okay, the same thing happens when it reaches the boiling point, and I need up here, right, to turn the water into steam. I need to add energy, even though there's no delta T, and the question is how much energy did I need to add? It is 2.3 times 10 to the 6 joules per kilogram. If I have 2 kilograms, I'll need 4.6 times 10 to the 6th joules. If I have 10 kilograms, I'll need 2.3 times 10 to the 7th joules of energy. So again, this is also latent heat, and I need to be able to just show you the different values for specific latent heat. So I'm seeing a couple of things I want to change here. So let's get rid of this, because this is wrong altogether. And I'm going to change this also. So specific latent heat of fusion is 3.3 times 10 to the power of 5 joules per kilogram. And my LV is 2.3 times 10 to the power of 6 joules per kilogram. 2.3, come on, joules per kilogram. So my numbers are in this chart here below, but again, it's a little bit different in our textbook. Our textbook uses 3.3 times 10 to the 5. But again, you can see that to melt aluminum, it happens at 2,500 degrees. Right? I can melt aluminum, turn it into a liquid puddle of aluminum at 3,000 degrees Celsius. And if I was to keep heating it, and heating it, and heating it, 4,000, 5,000, 6,000, till I got to 10,000, I still have liquid aluminum, and if I could heat it to 11,000, I'd go right through the boiling point, and I would turn all of that aluminum at 10,900 degrees. I would turn it all into aluminum gas. In aluminum gas, how do you turn a metal to a gas? The answer is you heat it a lot. Now, aluminum's a lot higher than some of the other metals. Notice down here that for gold, it's about 3,000 degrees. For lead, it's about 2,000 degrees. Right? But the temperature here doesn't matter, right? What I'm concerned about are these numbers here, right? The LV values, the latent heats of vaporization, and the LF values, the latent heats of fusion. So again, I can scratch out the melting points here and the boiling points, and I just need to use the LF values. Now notice, if I look at my cooling curve up here, right, just like the heating curve says as I'm heating it, Q equals MC delta T, Q equals ML. Q equals MC delta T, Q equals ML, Q equals MC delta T. The C value is the C value for steam, the C value for water, the C value for ice. Okay, down here I have the amount of latent heat, Q equals ML, using LF. Up here I'm going to use Q equals ML using LV. Let's look at the other side of the coin. If I take that same water vapor and I want to turn it into an ice cube, I have to do exactly the opposite. I have to cool it, Q equals MC delta T. I have to turn it back into liquid. I have to condense it, Q equals MLV. I have to cool it down to 0 degrees, right? Q equals MC delta T using the C value for water. I have to freeze it, Q equals ML using the LF value for water to ice. And then I need to Q equals MC delta T, cool the ice down to minus 10. Turns out that the L value here is the same as the L value here, except one is positive when I'm adding Q equals ML, and the other one will be a negative L value when I do Q equals ML, because just like the Q value is negative in here and negative in here because MC delta T is negative, Q equals ML will be negative in here and negative in here. So here I'm going to use the same LV value that I had for boiling water. It's the same except it's the negative value. Negative 2.3 times 10 to the 6 joules per kilogram that condenses. Down here, my LF, because it's going from a liquid to a solid, it's basically losing potential energy. That's what LF is talking about, is how much potential energy was being added to separate them into the new state. It's going to be minus 3.3 times 10 to the power of 5 joules per kilogram. So when I look at my L values, way down here, the L values are going to be plus or minus 3.3 times 10 to the 5 joules per kilogram, or plus or minus 2.3 times 10 to the 6 joules per kilogram, depending whether I'm adding energy or removing energy. If I'm adding, remember that energy is potential energy that I'm giving to that matter. Right? When I change states from a solid to a liquid, it is gaining potential energy. Right? Not kinetic energy, because kinetic energy is temperature. Right? So I'm gaining potential energy. Same thing when I go from a liquid to a gas, gaining energy, gaining potential energy. Not kinetic, not changing temperature, right? Just changing my state of matter. Okay, so let's look down at the bottom here. So I'm going to do 2 sample problems quickly, and then as soon as I'm done, I'm going to let you go to try some of these on your own. And then that basically is the end of Chapter 8. Oh, except there's a section on calorimetry. I may do a calorimetry question in a separate note. Okay, so for now, I'm going to do the 2 samples that are In the work package, I will leave you with these examples here to work on your own, and then these 5 questions to work on your own using Q equals ML. I always think when I see something that's undergoing a change of state, I always ask myself, is there a temperature change going on too? Right, so let's say it's 0 degrees outside, and some of the snow is starting to melt because I've reached, say, +1. Right, and as it reaches +1, what's going to happen to that snow? Well, the snow is actually, say, at -13 from the night before, so I'm going to start at minus 13, and I know it's going to warm up until it gets to 0. And then it's going to change states to liquid, and it's going to go up to 1 degree. I can't do this here. Oop. 1 degree. Right, so you'll see that I have to have 3 calculations for this question. One for the change of temperature of ice, one for the melting of the ice, one for the warming of the liquid water. Right, so I'm going to always do these things as an A, B, C. If I start with ice that's 0 degrees Celsius and I just want to warm it to 25, I'm going to have to melt it and warm it to 25. Here it's ice at 0. I'm going to have to LF, I'm going to have to change its state to liquid, and then I'm going to MC delta T, ML down here, and MC delta T up there. I have part A of my calculation and part B of my calculation. Ultimately, once I've got my separate Q values, right, MC delta T and ML, I just have to add them up because I have to add heat here to melt it and then add more heat here. So I just have to add the 2 heats together to get myself from here all the way to the end of my graph. All right, so that little sketch, right, again, probably 4 seconds worth of work, reminds you that sometimes how many steps of calculation you would require. Here I needed 3, here I needed 2, and if I'm looking up here, I actually needed 5. I have an A, B, C, D, E, right? So my quick sketch always reminds me how many calculations do I need to do. Okay, over here I have 5. A, B, C, D, E. Cooling, condensing, cooling, freezing, cooling. Okay, so let's go to the 2 questions that were in the samples in our booklet. Whoops. So I've got 2 samples here. The first one says, how much thermal energy is going to be released if I have 652 grams of molten lead, liquid lead, and it's going to turn into a solid. Notice it's not talking anything about temperature changes. It's just saying all I'm doing is I am solidifying. I am freezing, solidifying some liquid lead into solid lead. So if I was to look at the solution here, for sample 1, I have liquid lead that's going to freeze. That's it. Right, liquid lead. Okay, so I only have 1 calculation here, and that is my Q value for this A part is A times M times L. The question is it LF or LV? Remember, anytime I have a gas at one end or the other, I'm going to use LV, the specific latent heat of vaporization. And if I have a solid at either end, it's going to be LF. So in this case, because I'm going from a solid to a liquid, I'm going to have M times LF. We're told the mass of the lead is 0.652 kilograms. And the LF for lead is 2.3 times 10 to the 4. joules per kilogram. I can see that my kilograms and kilograms disappear, and I end up with a number. Okay, so let's do my math. 0.65 times 2.3 times 10 to the power of 4. And I'm getting 1.50 times 10 to the power of 4. Okay, and I'd say, okay, there we go. But I've got a problem here. Right? The problem is Q here is positive, which means I must have added energy. If I want to go from a liquid to a solid, do I have to add energy? Well, I don't know. Think about it for a minute the other way around. If I go from a solid to a liquid, what do I have to do? I have to melt it. I have to heat it. I have to give it energy. So if I'm going from a liquid to a solid, what is my freezer doing? It is removing energy from that water. In this case, removing energy from the liquid lead. So my answer had to be negative 1.5, and the reason is the LF value. Remember, even though the textbook says 2.3 times 10 to the power of 4, it's actually plus or minus 2.3 times 10 to the power of 4. In this case, it's negative because we're removing thermal energy from that lead. If I look at sample 2, so Q is 1.5 times 10 to the 4. If I look at sample 2 on the same page, so let's go to sample 2 there for a minute. It says ethyl alcohol at room temperature, so I need to know what it is. I know that it's absorbing energy. I know how much mass I have, and it is at 21.5 degrees C. It's going to be heated until it boils and turns into a vapor. So a couple of things have to happen here. Number one, I've got to warm it up to its boiling point. 100 degrees C? No. Ethyl alcohol isn't water. Ethyl alcohol actually boils at minus 130 degrees C. Oh, sorry, at 78 degrees C. It will boil at 78 degrees C. So I've got to warm it from 21.5 to 78, and then I've got to evaporate it. It doesn't say anything about heating the vapor, it just says turning it into a vapor. So I'm going to have to do two things here. So let's go back to my whiteboard. Okay, so we are given, let me get my question out here. Okay, we're given the mass of the ethyl alcohol. .135 kilograms. Now, notice what I'm having to do here before I do anything is to say, what is this question going to look like? I'm going to take my ethyl alcohol and warm it up to its boiling point and then turn it into a gas. So I have an A part of this question and a B part of this question. Now, the missing pieces here are the temperature that I started with, 21.5 degrees C, and what temperature it needs to be at in order to evaporate, and we can see that it is 78 degrees Celsius. It's actually 78.3. Now, we'll just go with the 78 from our textbook. So if I know what the temperature needs to be in order to evaporate, and I know how much matter I have, I can do my A part, Q for A. Because I'm seeing a delta T for A, I know I need to use the MC delta T formula. The mass is 0.135 joules per kilogram degree C times, with 0.135 kilograms. Sloppy. Times the C value for ethyl alcohol, which is 2.4 times 10 to the power of 2 times the temperature change, which is final temperature, minus 78, minus my starting temperature of minus 21.5 degrees Celsius. Okay, and if I do all of that math, I'm getting 1.89 times 10 to the 4 joules. Notice that my delta T is positive. Final is 78, initial was 21.5, so my delta T is positive, so my Q value is positive. That makes sense because I'm adding heat, and Q has to be positive. If I look at what's happening in part B, I've got a change of state, so I've got to use Q equals ml. Am I going to use LF or LV? Remember, LF is for solid-liquid changes of state. LV is for liquid-gas changes of state. Because I'm boiling or evaporating my ethyl alcohol, I'm going to use LV. So I'm going to use my mass here, 0.135 kilograms, times the L value for ethyl alcohol, which is 8.6 times 10 to the power of 5. Joules per kilogram. Notice that the kilograms disappear, so I'm getting an answer of 1.16 times 10 to the power of 5. Okay, and if I want to know what the total amount of energy is now, it's the amount of energy that I needed to warm the alcohol plus the amount of energy that I needed to evaporate the alcohol. So I'm going to add those two numbers, and I get a final answer of 1.3 times 10 to the 5 joules. Okay, so we're still using MC delta T here, but now we're adding our new values of new formula with specific latent heats of vaporization and fusion to calculate my Q values for my question. So I'm going to finish there for now. I will leave you with the questions in our textbook, which are here on pages 267 and 268, right? The examples, and then the end of chapter questions on page 277, right? And that should give you lots of practice to do those questions. If you're looking for a little more, there's questions 2, 3, and 4 on page 269. And again, remember all the answers for these questions, and these questions are at the back of the book, and these ones are actually done for you as you're working through them. All right, so I hope everything's well. I'm still working on, I know a number of you are looking for updated marks. I'm still working on it. I wanted to get the ISUs in there also before I sent your marks out, because that will largely give you